So we're going to look at QuickSort, which is another divide and conquer algorithm for sorting. In this lecture, we'll look only at an overview of QuickSort and how it works and the intuition behind it. In the next lecture, we'll follow it up with a more elaborate version which does in-place sorting. It turns out that doing in-place sorting without using extra space and so on is much more complex. So that's what the next lecture will cover. And in the third lecture, we will look at the analysis of QuickSort. So it turns out that the worst case complexity of QuickSort is order n squared. So it's in fact worse than in the worst case, worse than algorithms like merge sort that work in order n log n time. But it turns out that in the average case, QuickSort performs pretty well. It actually achieves order n log n complexity. And in fact, there's a randomized version of QuickSort that also works in order n log n expected time complexity. And in this, we assume that your algorithm has access to random bits, and then it can work well. But most importantly, it turns out that in practice, QuickSort works very well. It actually competes well with algorithms that have worst case complexity order n log n. The main difference between QuickSort and merge sort is the way the sorting problem is divided and conquered. Let's look at an example. 5, 3, 9, 2, 1, 7, 4, 8 is a list of numbers. If you look at merge sort, what it does is it first divides it into two halves, 5, 3, 9, 2, and 1, 7, 4, 8. And then it calls itself recursively to sort these two lists. And then it merges them, these sorted lists, into one longer sorted list. And we saw this algorithm merging to produce the longer list 1, 2, 3, 4, 5, 7, 8, 9. Right? So merge sort does this sorting by dividing the first list into two equal halves, and this division is actually a very simple operation, right? It just splits it into two parts. And the merging is more complex operation that it can be done in order n time, but it's a little more complex. Since it divides the list into two equal or roughly equal halves, merge sort achieves a worst case complexity of order n log n. So now let's look at QuickSort on the same example. 5, 3, 9, 2, 1, 7, 4, 8. So in QuickSort, what you do is you first pick an arbitrary element called the pivot P. Let's say we just pick the first element here, which is 5. Okay, so the choice of the pivot is actually important for the performance of the algorithm. We'll come back to this later. Let's now assume that the pivot is 5. Then what you do is you split the list into three parts. SL, which is the left list, contains of all elements of the list which are strictly less than the pivot. SM is the set of all elements of the list that are equal to the pivot, right? Since there could be multiplicities of elements in the list, there could be multiple occurrences of 5. So this might be this need not be a singleton list. And then you have SR, which is the set of all elements that are larger than P. Okay, so I can do this in one pass. I can just go through the elements of the list. If it's equal to the pivot, I throw it into SM. If it's less than, I throw it into SL. And then if it's larger, then I throw it into SR. So let's do that. 5 goes here. 3 goes to the left list. 9 goes to the last list. 2 and 1 go to the first list. 7 goes to the last list. 4 goes to the first list. And 8 goes to the last list. Right? Now I split into three parts. Now I'm going to call myself recursively on SL and SR to sort the sublists. And this would give me 1, 2, 3, 4 here. and 7, 8, 9 here. Now I can put these things back together since I know that the elements of the first list are strictly smaller than P, which is strictly smaller than the elements of SR. I can just merge these lists by concatenating them. I don't need to do a complex algorithm. I just concatenate these lists to get the sorted list 1, 2, 3, 4, 5, 7, 8, 9. So in some sense, this is the opposite of merge sort in the sense that I'm doing a slightly more complex operation in splitting the lists into two parts, right? But when I put them back together, the operation is much simpler, right? I just concatenate the lists. It turns out that depending on the choice of the pivot, these two lists, SL and SR, need not be even roughly half the original list, right? I mean, they can be very skewed. For example, if I had picked the element 2 to be the pivot instead of 5, then only one will get into SL, all the other elements will get into SR, and it results in a very skewed partition. And in fact, this is the reason why QuickSort has an order n squared worst case complexity. But it turns out that if you pick the pivot randomly, right? If you just don't pick it as a one fixed element, but if you pick it randomly, you can get a randomized algorithm of n log n expected time complexity. And in fact, even if you pick the pivot, deterministically, it turns out that the average case for quicksort is order n log n. So let's look at the quicksort algorithm. Um, quicksort gets an input which is a list of numbers. And what it does is first picks an element, an arbitrary element, P in S. Then it constructs three lists, SL, SM, SR, where SL is elements of S that are strictly less than P. SM are elements of S that are equal to P, and SR is the set of elements of S that are greater than P. And then it calls itself recursively to sort the lists SL and SR, and then it simply returns the concatenation of the lists SL, SM, and SR. The base case, of course, is that if S is empty, if S is empty, it's an empty list, then return S. It's already sorted. So we will see in the next lecture how to give an in-place algorithm to do especially this partitioning. The rest of the algorithm actually remains the same. The partitioning to do it in place, it requires a more complex algorithm, which we'll see in the next lecture. So this idea of taking a list of numbers S and choosing a pivot P, and then partitioning the list into three parts, SL, those elements less than P, SM, those numbers equal to P, and SR, those numbers larger than P, has other applications as well. For example, there is this famous problem called selection, which is you're given an input, a list of numbers, S, and you're given a number K, and you're asked to find which of these numbers is the kth smallest number in S. The selection problem, by the way, if you are given a list of numbers, of n numbers, then in fact the median is actually um, the kth smallest number, where k is roughly n by 2, right? So this is also the median finding problem is also similar to the selection problem. So now we can solve this by divide and conquer, because we can take the list S and you can split it up into these three parts. And then if k happens to be less than or equal to the size of SL, then I know that the kth smallest element is in SL. So then I can recursively call select on SL with k. Otherwise, if k is less than equal to SL plus SM, then I know that k is in SM. So in fact, then I know that the kth smallest um, element is the pivot P, because all the numbers in SM are equal to P. And the third case is that k is in SR, in which case I can select recursively run select on SR, but I have to reduce the k to by SL and SM. So if you follow this algorithm, it turns out that it has an average case linear time complexity, right? And in fact, using this similar ideas, you can improve on this algorithm to build a deterministic algorithm for selection that runs in linear time. So this part of the selection problem is not part of your syllabus, but I just wanted to tell you that this way of splitting according to a pivot has applications other than sorting.